Good day, everyone. My name is Brad Langdale. I'm here to talk to you about my good friend Atwood and his pulley. A few things to remember about pulleys to start off with. A single pulley is only going to change the direction of the force that's acting on a system. So really, it's not too complicated to deal with if you can keep that in mind. And the second thing that I like to remember when dealing with questions with a single pulley is we're going to be using a net force statement to solve these type of questions again. And in the second half of the dynamics unit in Physics 20, we do a lot of questions dealing with this idea of the net force or the total force, all of the forces added together acting on the system. So let's look at a problem. Two masses are suspended from a frictionless pulley by a rope as shown. Calculate A, the acceleration of the system, and B, the tension in the rope. So first we're going to find the acceleration of the system. Again, I'm going to draw a free body diagram of all of the forces acting on this system. I've got a force of gravity from the first mass. I'll call that force of gravity 1. And I've got a force of gravity from the second mass. I'll call that force of gravity 2. There's also forces of tension here in the rope, but I'm going to deal with those in part B. Now again, I'm going to use this pulley as just a device that's changing the direction of the force. So I'm going to, what I call with my students, straighten out the pulley by drawing the two forces collinear to one another up here, one going right, one going left. And it doesn't really matter which one is left and which one is right, to be truthful with you. But this is the way I'm going to start off with it here, with the force of gravity acting left and the acting left and the force of gravity 2 acting to the right. Now that I have that down, that's going to kind of serve as a reminder for later on when I do my net force statement. So my net force is the force of gravity 1 plus the force of gravity 2. Now I can do some substitutions. In place of the net force, I can write mass times acceleration. And this acceleration here is the acceleration I'm looking for in the question. In place of the force of gravity, I can write mass times acceleration due to gravity, and ditto for the second force of gravity. Now I need to throw some numbers in for my variables, and this is where some students can get confused. Let's start with the mass for the net force. Now because I'm looking for the acceleration of the system, that's of both the masses together, I'm going to have to use the sum of the two masses. So in this case, that's going to be 3 kilograms for my mass in the net force. So I'm going to add them together for the mass of the net force. For the force of gravity for object 1, well, that's 1 kilogram multiplied by 9.81 meters per second squared. And for the force of gravity 2, I guess that's 2 kilograms multiplied by 9.81 meters per second squared. Now, this step I always like to pause for a minute and make sure that I have all of my vector directions down. So I notice the force of gravity 1 is acting to the left. So this term is going to have to be a negative number. I'm going to put a negative in front of the 9.81 so that when I multiply it by 1 kilogram, it would become a negative vector. It means it's going to the left. The 2 kilogram mass, which represents force of gravity 2, is acting to the right. That's the positive direction. So I'm going to leave this as a positive 9.81 meters per second squared. Well, now all I have to do is determine what I get by multiplying together the two terms on the right-hand side and then adding the numbers and dividing by the total mass of 3 kilograms. So I think I can probably punch that into my calculator now at this stage. So 1 times negative 9.81 plus 2 times positive 9.81. I'm going to divide that all by 3 kilograms. So my acceleration is 3.27, and for significant digits, it'll be 3.3 meters per second squared. Now, a question a lot of students ask is what direction is that, positive or negative? Well, because the mass 2 is heavier, its acceleration will be downwards. It would drop. And mass 1 is lighter, its acceleration would be upwards. So it's the same acceleration, but one's positive, one's negative. So I usually write that as plus or minus 3.3 meters per second squared. And there we found the acceleration of the system. Part B, we have to find the tension in the rope. So for part B, I'm going to clear this off. I'm going to focus on just one of those two masses, and it doesn't really matter which one you deal with. So I'm just going to deal with the 1 kilogram mass. I think that seems like a easy place to start. And again, I'm going to do a free body diagram on it. Well, it had a force of gravity acting down on it. It also had a force of tension acting up, and that's what we're trying to solve for in this question. And the 1 kilogram block had an overall force, or a net force acting on it. And because it was the lighter of the two, it's going to move upwards, so that's my net force. So again, I can do my net force statement. Net force is force of gravity plus the force of tension. Now, what am I going to put in place of the net force? Well, it's still a mass times acceleration. 1 kilogram is my mass. And remember, my net acceleration from the last part of the problem was 3.3 meters per second squared. Because I'm dealing with the 1 kilogram mass and it's moving upwards, I'm going to leave that as a positive acceleration because the acceleration is going to be up. Boy, I'm going to run out of space here. The force of gravity, that's going to be 1 kilogram times negative 9.81 meters per second squared plus the force of tension. And that's what I'm solving for, so I don't have to substitute in anything for that. If I rearranged that statement, I'd get the force of tension equals 1 kilogram times 3.3 meters per second squared plus 1 kilogram times 9.81 meters per second squared. And I should, that would be correct. Now, I'll type it into my calculator. You might be wondering, well, where did the negative sign go, right? We had a negative here, and then it's gone. Well, because when I add it to the other side, this is going to be a positive term. If you wanted to, you could have just multiplied these numbers out at this step and got them as a single term. That might have made it easier for you. But I'm just going to do it all in my calculator to save myself some time. So 1 times 3.3 plus 1 times 9.81. So there we go. Looks like we're getting a force of tension of 13 newtons up. And if you would have used the 2 kilogram block, you would have gotten the exact same answer. The only difference would have been your net force would have been in the opposite direction, and you would have been using a different mass, but you would have gotten the same tension. So hopefully now you have a better understanding of how Atwood's pulley works. For more information on Atwood's pulley, we've got some notes on my website, www.ldindustries.ca.